The next chapter is the second part of interference. Remember, in the last chapter we studied the Young's double slit experiment. In this chapter we're going to study interference because of some other instruments. For example, a Lloyds mirror, a Fresnel's prism, and a lot of other interesting things. As you can see, for example, in the figure on your screen, there is one single slit, and then light is coming and falling on a mirror, and then the light from the mirror and the light from the slit are forming an interference pattern. So we'll study all interesting things like this in this chapter. Let's proceed. The first new method that we'll study is the Lloyd's mirror method of producing an interference pattern. You see, this is an alternative to the Young's double slit experiment. In this case, there is only one single slit, and light from this slit reaches the screen. However, a mirror is placed like this, as shown in the figure, at the base. Now, light from the source strikes the mirror, and then it strikes the screen. So as you can see, an interference pattern is now observed on the screen. Can you guess why an interference pattern is observed? Well, the reason is very simple. Because of the reflection of light from this mirror, an imaginary source S' is created here at this position. This source S' is at the same distance from the mirror as the original source S. Now light will be coming from two sources, the source S and the imaginary source S', and the light from these two sources will have a path difference, isn't it? As you can notice, this will be the path difference between the light from these two sources, correct? And this path difference will cause an interference pattern on the screen. Here we go. So at what positions will the maxima and minima be formed in the Lloyd's mirror method? They should be the same maxima and minima, right? After all, there are two sources here. The only difference is that one of the sources is imaginary. However, in this case, the final pattern obtained on the screen is slightly different from that obtained in the Young's double slit experiment. The reason is that when a ray gets reflected from a mirror, it suffers a phase difference of pi. So there is an extra phase difference of pi in this case. If you consider any point on the screen like this, then the net phase difference at that point will be the usual phase difference plus pi. This extra phase difference of pi, I repeat, will come because when any wave gets reflected from a mirror, it suffers a phase difference of pi. We had already learned this phenomena when we were studying wave mechanics, isn't it? Therefore, this phase difference will be equal to k delta x, where delta x is the path difference at any point, plus pi, correct? Now we already know what the path difference in the case of the Young's double slit experiment is. Remember, we had calculated that the path difference is x d divided by d, correct? So substituting the value of delta x by x d by d, this is what we get. 2 pi by lambda into dx by d plus pi. This pi is the extra factor. Now we know that for any particular maxima, the intensity at that particular point should be maximum. That is, the phase difference at that particular point should be equal to 2n pi, because when the phase difference is 2n pi, that's when the intensity at that point is maximum. Similarly, in case of a minima, the phase difference should be 2n plus 1 into pi, because when the phase difference is 2n plus 1 into pi, the intensity at that point is minimum. So we can equate this phase difference that you see on your screen to 2n pi to obtain the maxima, and to 2n plus 1 into pi to obtain the minima. So in case of maxima, 2 pi by lambda into dx by d plus pi will be equal to 2n pi. That gives us the value of x as n minus half into lambda d by d. So all the points which have x as n minus half into lambda d by d will be maxima. Similarly, when we equate this phase difference expression to 2n plus 1 pi, we get the value of x as n into lambda d by d. So again, all the points which will have their x coordinate of the form n into lambda d by d will be the minima. One interesting thing that you must have observed when you notice the expressions for the maxima and the minima in case of a Lloyd's mirror is that these are different from the Young's double slit maxima and the Young's double slit minima. In case of the Young's double slit experiment, points with x equal to this expression were the minima, and points with x equal to this expression were the maxima, correct? Remember, we used to say that the maxima are situated at 0, lambda by d, 2 lambda by d, and so on. In this case, the Young's double slit maxima become the minima for the Lloyd's mirror, and the Young's double slit minima become the maxima for the Lloyd's mirror. Interesting, isn't it? So as you can see, there will be a minima at 0. There will be a minima at lambda d by d, at 2 lambda d by d, 3 lambda d by d, and so on. You must note that the central fringe in this case is a dark fringe, that is, there is a minima at the origin. That's an interesting point to note. Similarly, at half into lambda d by d, 3 by 2 into lambda d by d, and 5 by 2 into lambda d by d, there will be maxima. These were the places where there were minima in the Young's double slit experiment. If you look closer at the fringe pattern, this is how it will look. At x equal to 0, you can see a minima, and you can see a maxima at minus half into d lambda by d and plus half into d lambda by d. You must note, however, that the fringe width does not change. As you can see, the difference between two maxima in this case is also capital D into lambda by d. So that was the concept of the Lloyd's mirror. Another interesting experiment is designed around an instrument called Fresnel's biprism. And let's study this modification of the Young's double slit experiment.